Hi everyone, so today we're going to be looking at our next lesson, and this lesson is going to be split into 3 parts because there is quite a lot of information. And this lesson is focusing on Le Chatelier's principle. And so when we work through this, you are going to have some time to work on obviously some worksheets that are associated with this lesson. Because it's split into 3 parts, you might not be able to answer all the questions right away that are given to you in your homework. So just go through them, find questions that we might have completed based off of the lesson, and then save the other ones for later. So this principle is seen as if there is a change, so any stress that is going to be put onto our system or our equation when it is seen at equilibrium, then the position is going to shift in the direction either left or right in order to reduce that stress. So if we have a reaction that is disturbed, it can reduce by either shifting to the right, so that means our reactants are going to decrease and our products are going to increase because of that shift to our right, or we can shift to the left, that is where our reactants increase now and our products decrease. So when we look at this shifting, we're looking at the shift in concentration. We're not looking at the shift of mass, we're looking at the shift of concentration. So if anything is disturbed when it's at equilibrium, we're going to have a change in shift in concentration of our reactants and products. So when we look at our reversible reactions at equilibrium, we can see it as like a seesaw. So there are 4 different disturbances. The first one, if there's an increase in concentration of our reactants, so that means we add reactants to our seesaw, then obviously our products are going to be less than our reactants. So in order to reduce that and reduce the stress, we have to reduce our reactants by shifting to the right, so we increase our products to reestablish that equilibrium. The second disturbance is a decrease in concentration of reactants. So the first 2 are focusing on just the reactants, whether we increase or decrease the concentration. So if we decrease the concentration of the reactants, then that means there's going to be more stress. So in order to reduce that, we increase the reactants by shifting to the left, and we will reduce our products. The third is based off of the concentration of products, so increasing our concentration of products. So in order to reduce that, we have to decrease the products, shift to the left, and this will increase our reactants. And then our fourth is a decrease in the concentration of products. So we remove the products. This causes an increase. And in order to reduce that stress, we increase the products by shifting to the right, by taking those reactants and putting them towards the products. So in summary, the first 2 are about reactants, so whether we increase or decrease the reactants. So if we increase the reactants, that means that in order to change that, we have to shift to the right and our products will increase. The second is a decrease in reactants. It will shift to the left in order to make sure that we increase our reactants and decrease our products. The third and fourth are focused on products. So we have an increase in products. That means the reaction is going to shift left to increase our reactants. And then disturbance 4 is a decrease in products, so we shift to the right in order to have a decrease in our reactants. So let's look at some examples. So we have N2 plus 3H2 reacts to produce 2NH3. So we are going to look at what happens when N2 has an added stress. So if it's at equilibrium, stress is added to N2, so that means there's an increase in N2. So when we are looking at equilibrium, this space here is all at equilibrium. The second we have an increase, then that means that we are not in equilibrium anymore. So we see an increase in our N2 right here. Because it's an increase in our reactants, that means that we are going to actually have to change our reaction because of that added stress on N2. So because we have an increase of N2, we need to decrease it by shifting to the right. So when we shift to the right, our H2 and N2, because they are our reactants, because there was an increase in N2, it's actually going to decrease. And our NH3, which is our products, is going to increase in order to maintain equilibrium. So we will see the following. So you'll see the slight increase in N2. You will see a decrease from there in our reactants. So there will not be a slight increase whatsoever of our H2 because there was no increase in it. It's just a decrease because we have to decrease our reactants. And we will increase our products because we are shifting to the right in order to reach equilibrium. And at this point right here, we have maintained now an equilibrium. So that is what happens in a situation like this. We can look at another example, very similar here. We have a decrease, a removed stress of H2. So we see that drop in H2 because there are reactants. We are going to have, in this situation here, we're going to have H2. We're trying to remove, and we remove the H2. We're trying to now increase the concentration of H2 by shifting to the left. Because H2 has decreased, we want to shift to the left in order to increase it. And so when we shift to the left, that means our H2 and N2 now are going to increase. So our H2 and N2 are now going to increase. So because we have an increase of reactants, that means our products are going to now decrease in order to reach equilibrium. And once they've leveled out, we now have a new equilibrium. As you can see there, this line is our new equilibrium. And this occurs over time because our H2 and N2 increase and our NH3 decrease. Next example here, same sort of situation, but now we have NH3 decrease. It's a removed stress. So because of that removed stress and it's a product, we need to increase it. So we're going to shift to the right in order to increase it. So in order to add more NH3, our reactants are going to decrease as well in order to have that shift. And now we reach a new equilibrium as N2 and H2 decrease, NH3 increases. Okay. Another example here, same sort of situation. We have O2 added stress. So because of that added stress on O2, it is in our products. So in order to reduce that, we shift to the left in order to try to reduce that stress because it was increased. So we shift to the left in order to change our concentration. So that means our O2 and our CO, which are our products, are going to decrease, and our CO2 is going to increase. And you can see that shift there. So you'll see a trend. We have one atom that is going to increase slightly because it's either an increase or decrease because of the added stress. And then if it's a reactant or product, the products, say for example in this situation, are going to decrease, and our reactants will be opposite and they will increase. So now as we continue on, we can see this is another example here. There was a little spelling error here. This is supposed to be Fe. So when we look at a situation like this, we add FeSN. So because of that, we are going to dissociate into FeNSCN. So therefore, there is an increase in the concentration of SNC because of it's an increased product. Okay, so because of that increase of SNC, we are going to shift to the left in order to reduce the stress of SNC increasing. Because SNC increased, we're going to reduce that by shifting to the left, adding more to our FeSNC because SCN, I keep saying the opposite, FeSCN, because FeSCN is our reactant. So because our product increased, we need to shift to the left in order to reach equilibrium, and that is what we will be doing. So the opposite of this, we add FeS. I don't know why it keeps doing this. FeSCN. same thing here, FeSCN. Oh, that was right. And then SCN and SCN. So because we add more to our FeSCN and it dissociates, we are going to shift to the right in order to form more Fe and SCN. And so what happens in a situation like this, the SCN will form a solid, and then the FeSCN, because of the reaction that takes place of going from FeSCN to Fe and then SCN, the dissociation, it shifts to the right. So we have an increase in this. We want to reduce that stress, so we need to increase our products as well. So what happens is that we actually try to increase the concentration of Fe because of what forms, okay? So as a result, we shift to the right. This is a little bit confusing, so don't worry about this too much. It's a little bit confusing. Just note that if we increase FeSCN, we will shift to the right, and same with the example before, as previously said. Because we are going to shift to the right, we decrease our reactants, we increase our products. That's just the synopsis of this. Now, example 7 and 8 are looking at solids. So, in a situation like this, we're condensing H2O gas, and we create actually a liquid. And so, because we are trying to reduce the stress of our reaction, we are actually going to increase the concentration of H2O. This is a gas, okay? As H2O does increase, Fe is a solid, and it is a solid. The concentration of it, as I mentioned at the very beginning, changes, okay? Sorry, the concentration does not change, but the mass actually increases of it. So, in a situation like this, okay, we have our H2, this is decreasing. We have Fe2O3, this is also a solid. The concentration doesn't change of it. It's still going to be concentrated as much as possible, but the mass is going to decrease. So because we have more of our products, more of our products than reactants, we want to decrease it. If it's a solid, once again, the concentration doesn't change, just the mass is going to change. And then the same thing with our products, because it's a solid, the mass is going to just increase, okay? Not actually the concentration of it. So just a little FYI to note that whenever we look at concentrations of solids, the concentration is not going to change of a solid, only the mass will change. So same sort of situation here. If we add Fe, which is a solid, okay, the concentration will not change, but we are still looking at the overall reaction. And because the concentration will not change, it will not shift and will remain at equilibrium. So our reactions will only shift if there's a concentration change. So if we look at solids and liquids, it's not going to change, but because the previous example we looked at gases, we looked at a gas and these were changing, then that means that we can have a concentration moving left or right. If we're looking specifically at solids, if we're adding more or less, we are not going to shift because the equilibrium stays the same. And then the final example here, we add HNO3. Oh, sorry, this is wrong. We're looking at this wrong. Ignore this. In a situation like this, we have stress on OH, okay? So what happens, in order to relieve that stress on the reaction, we try to increase the concentration of OH. And as a result, the reaction shifts to the right, so OH increases and Ca also increases because they are the products. Once again, we are not looking at our solid increasing or decreasing. We're looking at the stress of OH, which is not a solid or a liquid, and so therefore we can shift left or right. Okay, once again, our solid is still impacted. It's not via concentration, but it's via mass. So that means because we are shifting to the right, the mass of CaOH2 is going to decrease, not the concentration of it. Okay, so a little graph here. If we were to draw out our new equilibrium, the concentration of CaOH is going to stay the same because it is a solid. The only thing that's going to change is that we had OH, we had a decrease in OH. So because the stress on OH caused it to decrease, in order for it to reach equilibrium, it has to increase, as well as Ca increases as well because it is also a product. Okay, so just understand if we have a reactant product increasing or decreasing, what happens. If it increases, what direction does it shift in? What happens to our reactants and products? And understand that solids, their concentration will not change, only their mass will change. If we have an increase or a decrease of a solid, we will not be changing our equilibrium whatsoever. But if we have a solid in our equation and we add or decrease any other product or reactant that is not a solid, then we will see a change in equilibrium.